We are now looking at the vertex form of a quadratic function. So, given a function as I wrote it over here, f of x is equal to a is different from 0 times bracket x minus h squared plus k. The first thing we're going to do is to check that this is in fact a quadratic function. So we are going to expand the values we have over here and see if we can write it in the form that we know quadratic functions are. So we're going to have x squared minus 2 times hx plus h squared plus k. So this is a x squared minus 2ahx plus ah squared plus k. So that means that this is in fact a polynomial function of degree 2. Here this a is the main coefficient, which is different from 0 as we want. And the first thing we observe is that this is giving the concavity as in the standard form case. The concavity is going to be positive when a is greater than 0 and negative when a is less than 0. Then we have over here, this is going to be the independent term, so the coefficient that has no power of x. And remember that that was what we used to find the y-intercept. I think I call that for y-intercept. That's going to be 0 ah squared plus k. So we found two of the main features we need to find so far. We also need to find what is the axis of symmetry and the vertex and then the x-intercept. In this case, it's going to be the easiest to find what are the coordinates of the vertex before anything else, because, well, this is called the vertex form, and the vertex has coordinates h, k, where h and k were given in the original form. So now we have the vertex, we have that x equals h is the equation of the axis of symmetry. And the only feature we are missing to review how to find is the x-intercept. So we're going to want to solve, and I'm going to use the original form I wrote today, not the expanded one. We want to know when a times bracket x minus h squared plus k is equal to 0. This is going to be true if and only if a times the bracket x minus h all of it squared is equal to negative k. So that means that we need x minus h squared to be equal negative k over a. Now, if x minus h, all of that square is equal to negative k over a, that means that we have two choices for x minus h. It can be either the square root of negative k over a, or it can be the negative of that. So we write plus minus over here. So that means that x is going to be either h plus the square root of negative k divided by a, or x is going to be equal to h minus the square root of negative k over a. And of course, depending on what are the signs of k and a, we may have no solutions, exactly one solution, or two different real solutions. And well, for the x-intercept, if we want to write both coordinates, we have here what the x-coordinate has to be for our potential two different options. And the y-coordinate is 0, and h minus the square root 0 for the other one. And I want to draw your attention to what we did over here. So let me get a color here. How we solved this quadratic equation, because this is the key point of how we prove the formula for solving quadratic functions. Actually, what we do is to write the quadratic function in this form, the quadratic equation in this form, and then solve it in the same steps that we did over here. To finish this video, I want to look at how we convert from standard form to vertex form. So if we are given, let me change the color. If we are given a quadratic function of the form ax squared plus bx plus c, with a different from 0, how do we manage to write it as a times a bracket with x minus h all of it squared plus k? So the first step we are going to take is to take from our original form given over here a as a common factor. So we are going to be given we're going to be left with x squared plus b divided ax plus c divided a. What we want to do is to write this as a times, and then we're going to have some bracket that has x plus something else squared, and then we can have any number we want here, but just a number, no more variable x anymore. So that's what we want to achieve. So we want to find something of the form x plus something all of it squared, such that when we expand, we get the x squared that we have over here. We want that over there, and also these terms on x. So we want to also get plus b over a x. And then for the last part, we can get any number we want, because that's not going to be a problem, because if this is not the number we want, then that means we just need to compensate with a little bit eventually on this last real term over here. So if we have x plus, I don't know, let's say alpha, and we square it, we're going to get x squared plus 2 times alpha x plus alpha squared. That's the expansion of x plus alpha squared. So that means the middle term, the term with x, is going to have 2 times the product of the two terms of the binomial that we are expanding. So if we do it over here, we would like to see this middle term we have over here to have a number 2, because then we know if there is a 2, then the x is already here, and then the other factor is what we need to write in the dots that we are missing. So I'm going to write the number 2 here, we want it, but if I write the number 2 there, I also need to divide by 2 to compensate, so we don't change the value. So I multiply by 2 and I divide by 2. That's like not doing anything. But now this has the form we want, and this is telling us that what we want to write actually is x plus b divided 2a, all of that square. Let's check that this works. If we do this, we're going to get x squared plus 2 times the product of the terms of the binomial, so b over 2a times x plus b over 2a, all of that squared. So the 2 cancel, and we got what we want. This is equal to x squared plus b divided by ax plus b divided by 2a, all of that squared. That means that we can isolate this part, x squared plus b over 2ax. This is equal to, we have on the other side the perfect square we wanted, x plus b over 2a, all of that square, and then I need to subtract the b over 2a square that is coming from here. Why did I do that? Because now I'm going to go back to what we had here. So we are saying that f of x is equal to, we have a outside the brackets, and then inside the bracket instead of writing the first two terms, I'm going to write it as I did it here with the perfect square. So I'm going to write x plus b over 2a, all of it square, minus b over 2a, all of that square, plus there was a last term. The last term is here. Look at it. C over a. Yeah. So this is what we want. Let's write this one more time over here. We have an a outside, and then we have a term x. Well, we wanted something with negative, right? So let's write minus negative b over 2a, all of that squared, and then plus I'm going to multiply the a inside these two last terms. So we're going to have c minus, and then we're going to have b squared over 4a. Before a squared, but there's an a canceling out, so that's what is left. So that means that this negative b over 2a, that's my value for h. And that's good because we say that h has to be the one that gives us x equals h is the axis of symmetry, and we know that in the standard form the axis of symmetry is x equals minus b over 2a, so good, that's what we know. And then this over here is the value of k for our vertex form.